Is going to take a quick look at a mobile phone charger, a USB charger, which you have seen before, I'm sure. And what happened was that this was used by my wife to charge a phone, and she found that after a while the phone wasn't charging, or it would be only partially charging, and we were trying to see what was wrong. So the first place to look was the USB-C socket in the phone, and it was fine. There was no fluff, so there was no electrical issue that we could tell over there. We swapped the charging cable just to be sure, and what we found was that as we jiggled the plug of that cable in the USB socket of the charger here, that the phone would start and stop charging. So it was an intermittent fault. What could be the cause? Well, possibly with the stress of plugging and unplugging the cable into the socket. We were expecting, or I was expecting, that the electrical connections, maybe the solder joints or the tracks, would have come loose from the PCB, and because of that, the electrical connection wasn't good anymore. So since it wasn't working, I thought I'd just have a look inside. Now, at this point, here's the warning. When you are playing with things which plug into the wall socket with high voltage, it is dangerous. So do not do this. And I'm doing this for two reasons. One is my own reflection on what happened, and the other is for just information only. So do not do this yourself. So the charger looks like any other generic charger. It seems to show a brand name, but obviously they would not have built it themselves and would have just got it from a supplier. In this case, it says it's made in Vietnam, and it has 9 volts and 5 volts as the output. To open it up, I kind of prized off the lid at the end, and you can see the electrical contacts for the live and neutral that go into the wall socket. So looking from this direction, it has a retractable plastic earth or ground pin, and you've got neutral on this side and live on this side, and the way that the board fits is kind of vertically. It slides into these slots here, these guide slots, and the end of it, as you can see, there are 2 solder pads, one labeled N that makes contact with the clip for the neutral pin on here, and one labeled L there, and the solder pad makes contact with the clip for the live over here. This is the view of the top, I suppose you could call it, of the board. And we've got what looks like an isolation transformer over here, some electrolytic capacitors, an inductor there, and a couple of safety components. You can see it says NTC over there. You can see the USB socket is connected vertically, or it stands vertically from the board, and it has a plastic shroud with a bit of an L-shaped thing. The L shape extends all the way to this side as well, and we will see that in more detail later on. Now, if I get around to it, I'll try and reverse engineer the circuit or do a bit more of a teardown of the electronics. But in the meantime, this is just a quick overview of what I can find by looking at the board itself very quickly. Now, we can't see very much, or as much as I would like to, because of the angle of the lighting, and also because of the plastic shroud around the USB socket. So we're going to turn this around, as it were, and I've got another photograph, but just to show the relationship. So I'm going to turn this around so that we've got the USB on top. And now we can see the slot that's been cut into the board quite clearly there. And the plastic shroud, which was around the USB socket, also had a plastic piece which inserted into the slot over here. Right, now we turn it over, and we see lots of surface mount components on this side, And there are a few interesting things to note. One is that on the silk screen, they actually show the separation for the high voltage safety isolation. So it says what looks like 6.6 mm over here, 3 mm over here, which is interesting. It's a lot closer, and 6 mm over here. And you have the slot cut into the PCB here. So my guess then is that you can see this is live and neutral. We've got a couple more, or well, one more clear separation component, and it is this one over here, which is probably an optocoupler for the control. And this does the voltage control to make it a universal 110, 120, all the way up to 240 volts AC input, and the 5 volts or 9 volts coming through the USB. So my guess would be that from about here, and you can see there's a separation here, into the cut slot over there, down through this section here, which is the optocoupler, also providing electrical isolation, and we can see 6.6 mm down to here. This is the safety, or the safety low voltage part of it. So from about here down this section of the board, the top right hand quadrant, if you like, corner of the board is the safety, and everything on this side is the high voltage. And you've got a ground pin or an earthing pin, which will be probably on, not used except for probably the safety, but I wouldn't say that for sure until I can see, until I take a closer look. Now, immediately, we can see a few components. So I said this one, which is probably an optocoupler. We've got this, which is a bridge rectifier. And the point that I was trying to make was that immediately we can see that there are problems in the manufacturing of the board. We've got this surface mount component, which is right at the end rather than in the middle of the solder pads. You can probably notice some really awful soldering. And just the equivalent of the high voltage or the isolation transformer, you've got one end over here. So this is the safety end of the transformer, of the yellow transformer that we saw. And this is the high voltage end of it. Now, as I was saying, you can see some awful work. We'll just have a look at a slightly different angle and it will be even clearer. Right, at this angle with the light, you can see just how bad the soldering is. All the through-hole components are really awfully done. The surface mount components don't seem to be too bad, or there's enough solder, the components are placed or seated correctly, but for the through-hole pins or leads, we can see just how awful it is. On this point, you can see that it's so badly soldered that it's crystallized. Likewise, let's see over here, it's crystallized here and here as well. So it's not just cold joints, it's kind of extreme cold joints. Or it must have been moving or something while it was cooling down. And here we've got some cold joints over here as well. We've got the components which were cut to wrong lengths. So this one is bent over here. So sorry, it's a bit out of focus. But you've got one that is bent over here. We've got one which is sticking out way too far compared to the others as well. We've got some solder joints with insufficient solder. So you can just about make out here as well that there's not enough solder in there. And possibly here as well, but it's just eclipsed by the cold joint. Let's see if we can see there were one or two with not enough solder in them. We can see it in another shot, I think, or in the vertical shot. So since I had the board out, I thought, well, I'll take my soldering iron to it. I wasn't sure if this was caused by corrosion necessarily. And it was also obviously all the through-hole solder joints which had the problems. Now, there is no way to confirm, at least immediately, whether this was done by manual soldering or whether this was some form of selective wave soldering, but just judging by how inconsistent as well as bad the joints are, it's probably a case of manual soldering. So I took my soldering iron to it and a little bit of solder as well. It wasn't an awful lot of work. Melted down the solder, added a little bit more where needed. And quite surprisingly, that seemed to solve all the solder joint problems. So after doing the soldering, you can see that everything basically has been solved. So I will do a side by side, and you can see the difference. Right, so we've got side by side here against the brown background that is before soldering, against the blue is after my rework. And what you can see is that just applying some nice heat and possibly a little bit of solder solved all these crystallized joints. Now, nice and shiny, you've got a cone shaped bit of solder, which is just the right amount. I clipped off the leads which had been left for too long. So this one here is now better. Where was the other one now? The one here, which is so bad that it was bent. I'm not sure what the scratch is. I didn't check to see whether this was caused by the manufacturing, or I may have caused that as I was withdrawing the board from the housing. But anyway, I've redone the solder, clipped the lead off, so now this looks a lot better. And in these cases where there's hardly enough solder to fill the through hole, I filled that up as well. So all the joints, as far as I could find them, I've reworked them, and it seems to have solved the problem. So at least visually, everything seems to have improved. So everything with slightly grainy solder, indicating cold joints over here. If you look at the equivalent, it's all nice and shiny. And this one is awful. On this side, now problem solved. I've not bothered to remove the flux, but it seemed to be good enough. And ironically, my initial fear that the USB socket had come loose, or maybe had lifted the tracks completely from the board, which I thought had caused the intermittent connections. Well, it looks fine, and it would probably benefit from a little bit more solder, but on the whole, it seemed okay, so I didn't bother reworking that. But other than that, all I did was apply a bit of hot iron, a little bit of solder, and the board now looks a lot nicer. So I replaced the shrouding around the USB socket, which had the L-shaped piece here that went into the slot, and that gave or restored the isolation that was needed. So it's interesting to consider how and what they've done with the isolation using two things. So to begin with, if you like, they used just physical isolation of the board. So we use blue since the PCB there is blue. So if we look at the board end on, as it were, okay? So the way that they have done the isolation, what color shall we use for the PCB track? Let's use this color for the PCB track. So if you had a track here, so again, it's end on, and what they have done is, for a lot of the cases or situations on the board, they had a separation of 3 to 6 millimeters, and that gives you several kilovolts isolation quite nicely. But when it came to the area around the USB, I think they could not, for whatever reason, give the same amount of isolation across the board. So what they did then was to slice through the board, that L shape, and so now you also have a physical gap across or in the board itself. So now there is an actual removal of all material, and you've got the space there. And what they did then was to include or to insert a physical piece of plastic vertically through there. And that could be, as I was saying, because they couldn't separate the tracks between the low voltage and the high voltage side. So it could be something like this. And they could not get their 3 to 6 mm there for the voltage isolation. But with the plastic piece in place, then what happens is that the actual surface distance from one side of the, let's say, the safety to the high voltage, now is nicely 3 to 6 mm or even more, because the actual surface distance will be from there to there, and the distance of the length of this red line, if you like, which is the surface distance going around the plastic insert, gives them the isolation that they need. And at the end of it, I thought, well, I'll just put it in and try. So again, this is a warning. This is not something that you should do. I'm only doing this, and I did this very carefully, and I'm only showing this for my own reflection and for information purposes, but do not do this yourself. I plugged in a phone, jiggled the socket, and it was very reliable, and it was a case not to do with the USB socket coming loose after repeated cycles of plugging and unplugging. The USB socket was fine. It was just awful, my guess, manual soldering of the through-hole components and the through-hole leads, and it was just waiting to start failing as it got into the field, which is a bit of a disappointment. I would have thought that a big brand name would have chosen a supplier which had better outgoing QC, but to be fair as well, I'm not sure where we got this USB charger, and who knows if it was off some well-known online purchasing site. It could have well been an imitation. But problem solved by soldering, and it was all the through-hole components, nothing to do with the USB socket.